Hello. On this lecture we will see how to train variational autoencoders. And we will also meet the underlying theory. This will be a long and likely a bit challenging lecture, so try to keep awake. Before the formal version, first an informal version of VAE training. If there's one thing to understand about training these things, it's the loss function. A model is trained to do two things at the same time. First, to reconstruct the input data as accurately as possible, just like the standard autoencoder did. This makes immediate intuitive sense. And for that reason we need a reconstruction loss, which quantifies how different the reconstructed output is from the original input. Or in probabilistic words, how likely it is that the original data was generated by the reconstruction process. While the squared error is a common choice for continuous data, binary cross entropy can also be effectively used as a reconstruction loss if the data values are scaled to the unit range. There are good theoretical foundations for both of these choices. Secondly, we want to make sure that the learned latent representations, those learned distributions, are close to the standard normal distribution, zero mean unit variance. Such a comparison is now possible because the encoder actually gives us a distribution, or at least its parameters, which can then be compared to any other known distribution using well-known mathematical tools. The penalty term for this dissimilarity of distributions is the Kullback-Leibler divergence, which is a standard measure for the difference between two probability distributions. In our case, the one defined by the encoder output and the standard distribution. This seemingly unusual constraint has profound implications for the model's behavior and its ability to generate new data. Later on, we will see that there are also deep theoretical reasons for making this constraint. In practice, its effects are as follows. First, it acts like a regularization term. As you know, the primary purpose of any such term is to prevent the model from overfitting. In the context of VAEs, this means preventing the encoder from learning overly complex mappings or distributions that perfectly reconstruct the training data but fail to generalize. Second, it promotes a smoother latent space. By encouraging the encoded distributions to have low variance and a mean close to zero, we encourage the model to learn smoother and more continuous representations, where small changes in the latent space lead only gradual changes in the generated output. Finally, it also encourages so-called disentanglement. A disentangled representation is such that each dimension in the latent space corresponds to a distinct independent factor of variation present in the data, like character pose or the direction of lightning. By ensuring the encoded distributions are centered around the origin of the latent space, we encourage the model to learn such disentangled representations, making the latent space easier to understand and control. Intuitively, since the encoder has less freedom to encode each data point in some highly specific way, it is forced to find some more general and efficient representations. When one has less room to operate, one must use it wisely. These two component losses, make up the VAE loss function. We can simply sum them up, but usually they are combined with hyperparameter weights to control their influence on training. For instance, in so-called beta VAE, the KL divergence term is multiplied by hyperparameter beta, which allows us to prioritize either reconstruction accuracy by using a lower value or the disentanglement of the latent space by using a higher value. The best value is highly dependent on the specific use case, and finding it typically involves, as with all hyperparameters, empirical tuning. Let's next recall how these component losses, the reconstruction losses and the KL divergence are defined. As with the standard autoencoders, our reconstruction losses are the binary cross entropy and the squared error. You should be aware that both of them have strong connections to the log likelihood of our data. Squared error when we assume that data has a normal distribution, and the binary cross entropy when we assume that the data follows a Bernoulli distribution. Minimizing the loss function between the original and reconstructed data is then, as known, equivalent to maximizing the likelihood of observing the original data given the model's learned data distribution. We should be able to easily implement either one of these formulas. Kullback-Leibler divergence is a statistical measure that quantifies the difference between two given probability distributions, here P and Q. As you can see, the formula for the general case involves calculating an integral. Although this formula has a closed form solution when both of the distributions are normal, the general multivariate case involves computing inverses and determinants of the covariance matrices, both computationally expensive operations. The diagonal case is remarkably simpler and faster to compute. As seen in the lower formula, simple vector operations are sufficient. We should be able to implement this with some vector thinking. Then to the promised theoretical discussion. Why in the first place did the VAE inventors end up with this kind of loss function, a combination of two losses? The answer is known as the evidence lower bound, or ELBO for short. ELBO transforms the impossible task of calculating exact probabilities for high-dimensional data to a tractable problem by giving us a lower bound on the log likelihood of our data that can be computed or approximated with, say, if not easily, at least with relative ease. It's a true game changer for many machine learning applications. If we are able to maximize this tractable lower bound, we indirectly maximize the true but intractable likelihood. If its lower bound raises, it has no other choice but to raise itself. I wanted to understand how the ELBO can be a lower bound to something we don't know anything about. It sounds like magic or like snake oil. This understanding required working painstakingly through the whole derivation from the initial log likelihood to the final usable form of ELBO. For ordinary people, it is enough to remember the first formula and the last formula. The last formula, called ELBO, is a lower bound for the first formula, the intractable log likelihood of the data. For non-ordinary people like university students, they want to know how the last line is derived from the first. This slide isn't just mathematics, it's a journey from confusion to understanding, or from complexity to clarity. We turn an intractable problem into something we can actually work with. And if you understand this, you also understand how to use ELBO and why it works. Let's see. At the beginning is the log likelihood of the data, the intractable. We cleverly express the same thing by introducing a latent variable z and noticing that p of x is the marginal distribution of the joint distribution. Marginal distribution achieved by integrating over all possible z. Still, cleverly, we multiply and divide by a new conditional distribution q of z given x. This q will later on be called as variational distribution. Second, now that we introduced distribution q, we can rewrite the integral in terms of an expectation under q. This because expectations have some useful properties which we want to exploit later. There's a quite well-known theorem of mathematics called Jensen's inequality, originally defined for integrals, but applicable to expectations in the context of density functions, and that allows us to move a function inside its expectation argument. For concave functions like logarithm, the equal sign must be replaced by less than or equal while doing this move of function. This is where the transition from the exact log likelihood to its lower bound, which is why many textbooks define ELBO at this point and stop the derivation here. So here happens the transition from exactness to lower boundness. Next, we simply apply the properties of logarithms and transform the division to a subtraction. This step helps in breaking down the problem into components that can be treated separately. I hope you all know Bayes' theorem. It tells us how to get rid of the joint distribution by decomposing it. Now logarithm of a product equals the sum of logarithms. This allows us to separate the likelihood p of x given z from the prior distribution of z, p of z. Now that all terms are separated, we can rearrange them a bit. Expectation of a sum is a sum of expectations. We replace addition by negating the second term and subtracting it. In this way, we can construct the formula of the KL divergence in the latter expectation. Feel free to compare to the definition of KL divergence. Now, replacing the second term with its KL version gives us the last formulation, the ELBO. We have now derived a possibly tractable lower bound to an intractable problem. Much, of course, depends on the choice of q of z given x, and actually on the other two distributions in this final ELBO formula. We next consider design choices for all of these. Let's start by discussing the variational distribution, Q. The word variational implies that we should somehow be able to vary this distribution. And we know of a way of doing that by using parameterized distributions. In order to make the impossible possible, the variational must be possible, that is, tractable. In practice, this means that it allows for efficient sampling. In a parameterized family of distributions, we are looking for the parameter values that maximize the ELBO. And maximizing ELBO means adjusting the parameters of Q to increase the likelihood of the data under the model. As you know, this is a typical machine learning task. It's also a useful mental image of thinking of Q as an approximation of the true posterior p of z given x, the perfect mapping from data space to the latent space. This perfectness inherently suggests that it has captured the best possible high-level properties of the data, so it can be represented properly in the low-dimensional latent space. The better our Q is trained to capture the high-level properties of the data, the closer we can expect it to approximate the true best possible posterior distribution. There are still two pieces missing. First, there is p of x given z, the probability of observing data x given the latent value z. Computing this value, like the overall data likelihood, is intractable. How do we get forward in this part? Can we apply ELBO again? When we applied it to p of x, we were left with this intractable p of x given z. Apparently the same will happen if we do it again. It would not resolve the intractability issue. We need something else, something simpler, even if it's more approximate. What is done in practice is to find an approximation, say p prime of p. And to find a good approximation, parameterized models and machine learning is, again, the most promising way. Similarly to the variational distribution, we need to find the best parameter values for this approximation model, p prime. Consider a model that outputs parameters of a distribution over data for each latent variable z. Different values of z lead likely to different parameter values. Since we are now working in the high-dimensional data dimension, it is clear that, assuming multivariate Gaussian, the covariance matrices would be of astronomical size. Hence, it is natural to make some simplifying assumptions. We can restrict covariances to diagonal or isotropic. In the latter case, it suffices that our model simply outputs a distribution mean for each latent valued Z. How to train such a model? The ELBO term tells us to maximize the expectation of log of p of x given Z, which is now approximated by our p prime. Given that Z is drawn from the variational distribution Q. Now, if you look at p prime of x given Z and Q of Z given x, that is the same x in both of its appearances. If we assume that p prime is an isotropic Gaussian, maximizing the log likelihood is equivalent to minimizing the squared error between x and the mean of p prime. And the mean of p prime of x given Z is exactly what our model for learning p prime outputs. To summarize, given a sample Z, use the model to predict its estimate for the mean, and then compute the squared error of the predicted mean and the original data. When we sample such Z for enough many times, the averages of these squared errors approach the expectation in the ELBO formula. This process is known as Monte Carlo sampling. The reason for such a lengthy discussion about this p of x given Z is that the task of approximating this true posterior is explained extremely poorly or totally skipped in all textbooks I have seen, although it is a fundamental aspect of variational inference. Then to the final missing piece, p of Z, the prior for the latent space structure. Our prior belief about the distribution of the latent variables. This is typically assumed to follow the standard normal distribution. What's the justification? The isotropic or spherical nature of the normal distribution ensures that no particular direction in the latent space is favored over another, unless the data strongly suggests otherwise. And of course, this assumption greatly simplifies our computations. Empirically, this choice has been shown to work well across various applications. This choice is also motivated by the principle of indifference, also known as the principle of insufficient reason. In the absence of any specific knowledge about the latent space, all possible values should be treated as equally likely. It should now be clear that the VAE loss function is a specific instance of the general ELBO formula. In the VAE framework, the encoder learns the variational distribution Q of Z given X, while the decoder learns an approximation P prime of the generative distribution P. The reconstruction loss corresponds to the expected conditional likelihood of our data, and the KL divergence term represents the KL divergence between the diagonal Gaussian output from the encoder and the prior standard distribution. As it is more typical in machine learning to minimize than maximize. We minimize the negative of ELBO. As seen above, the expectation over the log likelihood in the first ELBO term is simplified significantly when we assume an isotropic Gaussian distribution for the decoder outputs p prime of x given z. This simplifying assumption is justified not only by its convenience, leading to simpler calculations and more efficient training, but also because it has proven to be a reasonable approximation in many cases, especially when dealing with continuous data, where noise is often modeled as Gaussian due to the central limit theorem. Recall that central limit theorem states that the sum of many independent random variables tends to be normally distributed, supporting why this assumption often holds in real-world scenarios. If we assume that p prime is an isotropic Gaussian with mean mu of z, the log likelihood log p prime is equivalent up to a constant to the squared distance between this mean and x. We define the decoder output as this mean, and this is what the decoder aims to learn in its training. A similar analysis applies to Bernoulli distributions, where the log likelihood becomes proportional to the binary cross entropy. To concretize, loss computations in the decoder proceed as follows. Given input z, a sampled encoding of the original data x, the decoder reconstructs as some hat x. This hat x is the decoder's current approximation of the mean mu of z, and we use it to estimate the log likelihood of the original data. This is done simply by computing the squared error between the reconstruction and the original. This single sample value provides a noisy estimate of the expected reconstruction loss. Now, in each training iteration, we sample a different latent code z for each data point x. The training process of VAE model itself induces a form of Monte Carlo sampling. We are effectively averaging over many samples of z, which provides a good approximation of the true expectation. Finally, a few words about the second term, the KL divergence. We have seen how this VAE-specific divergence term arises from the general ELBO. When the variational distribution is diagonal and the prior follows the standard distribution, the KL divergence has a simple closed-form solution with an efficient implementation. From this earlier slide, we see that in this special case, all we need are simple vector operations. We are now ready not only to implement a variational autoencoder, but also to understand what we implemented. Meet you on the next lecture, where we build, train and use a VAE. See you.